This video is an introduction to binomial expansion. And there's a lot of interesting things about binomial expansion, and we may have to just view this as an introduction and just get as far as we can. The first thing to understand, of course, is what it means that we're going to take this x plus y to the fourth here, and we are going to expand it. Now, of course, you could work this out as x plus 4 times x plus 4 and do that 4 times, but I hope that you can certainly see that that would be a pretty painstaking and tedious process, particularly if this exponent here, I mean, if we increased that 5, 6, 7, whatever, that's not something that is really a calculation that we want to spend our time doing. And what we have to deal with this is something called the binomial theorem. So binomial expansion, I guess I should amend this or append this and say that this is we're looking at in this lesson we're looking at the binomial theorem, which is a method for expanding binomials. Now, what we're going to notice here is that if I were to expand this, that I am going to have an x to the fourth term to begin with, and I am going to end up with an y to the fourth term. So hopefully you can see that that's what would happen, and then I'm going to have a series of terms in between. Another thing to notice is that we are going to, whatever the exponent is, so here of course our exponent is the 4, whatever that exponent is, we're going to have one more term than that. So if the exponent is 4, we're looking for 5 terms. So actually I should take one of these out down here, and we see that I would want to be filling in so that I end up with 5 terms, 2 of which are x to the fourth and y to the fourth, and then I'm going to have 3 other terms here as well. Now, the filling in these terms follows a very clear pattern, and this is what the theorem is about. That the pattern is that we're going to have x to the fourth for the first term, and then we're going to have x to the third for the next term, and then we're going to have x squared, and then it's going to drop to x to the first, and then it's going to drop to, it really drops to x to the 0, right? But we don't really need to write that. So I end up with x to the 0, y to the fourth here. And you see this x to the 0, of course, that is going to turn out to be 1. So we don't actually need to write the x to the 0, right? And then if I work from the other direction, you see we have the y to the fourth here, and that's going to increase, or it's going to decrease, I should say, as I move from right to left, and I can fill in those terms, the y terms that would occur in the expansion. So y to the fourth and y to the third, and then in the next term it's y to the second, and then the next term it's y to the first, and then here again it would have y to the 0, which of course we don't need to write that term because y to the 0 is 1. So let's go ahead and take that out, and let's take out this x to the 0 over here. We don't need to write that. Now, each of these terms is also going to have a coefficient. So there's a coefficient here, and there's actually a coefficient on the first one as well. A coefficient here, a coefficient here, and a coefficient here. Now, you may recall from some prior work with this that the coefficient on the first term is 1. So again, we don't really need to write that. The coefficient on the last term is 1. Again, we don't need to write that. And then we have these coefficients in the subsequent terms, or in these terms that are in between. Well, the first thing that you might recall, and something that's interesting about this, is that this coefficient here that I'm going to include in the expansion is going to match whatever the exponent is. So if you saw me write that in there, this coefficient right here is a 4 because the exponent, or not because, but it is the same as the exponent that is on the binomial that was given. And then also something to notice is that there is a symmetry to the coefficients. So you notice that this first coefficient is 1 and the last coefficient is 1. And the second coefficient is 4, therefore the second last coefficient is also going to be a 4 because there's a symmetry to these coefficients. So the only thing that I'm left with to find is this middle coefficient in our expansion. Now you probably have learned a method for finding these. You might remember this Pascal's triangle, this as Pascal's triangle, right? So you should have learned this in an intermediate algebra and algebra 2 class, Pascal's triangle. And Pascal's triangle would give us the coefficient that we're looking for. It gives this coefficient in this row right here. Does that look familiar? You see the 1, the 4, the 4, the 1, and then of course the 6. How do I know what row to go to? Maybe because I know I need the row where there are going to be 5 numbers, because I was going to have 5 terms in my expansion. Maybe I go to the row that the second number matches the second number matches the exponent of my expansion. And that would be another way to take me to the correct row. And we see that the missing coefficient that we're looking for is 6. So we'll go back to our expression and we'll plug in the 6 that was missing. Okay? So that should all look pretty familiar, I would think. Here's another one that we're going to look at, and it's just, there's a little bit more involved binomial that we're going to take a look at, and I think I'm going to probably go ahead. I want to do a little bit of a change here from what I've got. Let's go ahead and do that to the 6th power. And so I'm going to have 7 terms. I know that the first term is going to be the 2x to the 6th power, and I know that the last term, I'm going to go all the way over here to the right and give myself this last term is going to be 3 to the 6th power. And then in between, see if you can track me applying what we have learned about the expansion up to this point. So the first coefficient is going to be 6, all right? The 2x is going to drop to the 5th power, and then I'm going to bring in the 3 to the 1st power. And then on the next one, I need the coefficient. The 2x is going to drop to the 4th power. The 3 is going to go up to the 2nd power. And then another term, the 2x, is going to go to the 3rd power. I'm going to run out of space over here, so I'm going to take this 3 to the 6th out. And then the 3 is going to go up to the 3rd power. And here, you know what I just did? I just did a little check for myself to make sure that I was keeping track of the pattern. I thought about these coefficients and said, is the sum of those coefficients equal to 6? Because I know that that's not coefficients, the exponents. The sum of the exponents equal to 6, because I know that that's got to carry through every term. The sum of the exponents has got to be 6, matching the 6 from the original exponent. So that was just a little check that I did that I wanted to point out. And then we're going to continue here to 2x squared, and then we're up to 3 to the 4th plus 2x to the 1st, 3 to the 5th, and then finally we get to the 3 to the 6th. And I didn't leave a space. I stopped leaving a space for myself. I need a coefficient there, and I need a coefficient in here. I think I might be able to squeeze that in. Do you know what that coefficient is that's going to go? Yes, that coefficient. Do you know what that coefficient is? Maybe you see that it's going to be the 6 because of the symmetry. And I'll address that again in a moment here. That'll be plus 6. So again, remember the symmetry of the coefficients. So this coefficient here is 1, all right? And I'm picking up some coefficient from the 2, but that's from the binomial. So and that's not what I'm talking about. I'm not talking about the 2. So I have the 1 here, and then the symmetry puts a 1 all the way at the end. I have the 6 here, and then the symmetry puts a 6 with the second to the last term. This looks like it's a little confusing. Let me erase that and rewrite it. Okay, and a 4 there. Okay, so I need these other coefficients now. Now, again, I could go to Pascal's triangle, and what do I need? I need this next row, right? I need this 1, 6, that row here. But you can imagine that that starts to get a little bit difficult if the exponents keep increasing and increasing. So we have a way to deal with that. Now, I don't know how much time I'm going to have because of space and time limitations here, but I'm going to show you that you might recall that there was a method for doing this that involved factorials. Like if I wanted to do this coefficient here, so say I wanted to do this coefficient, you might have learned in Algebra 2 that we would do 4 factorial over 2 factorial, 2 factorial, all right? Whether you remember that or not, that was something that you might have seen. And so there's this way of doing that involves factorials. But there's a little bit more concise way of expressing what should go there using combinatorics. So this, let me see if I can squeeze this in here. It's a C, and then there's a 4 and a 2. Okay? No, it's not a 4. It's a 6. So I want a 6 in here. Got my plus C. All right, now what is that? Now I made an error when I showed you that factorial method because I gave you a 4 factorial, but it should be a 6 factorial. So what does this mean? Let's go ahead and take a look at that. This means the factorial that I was talking about before. So 6C2, and that's not the way you read it. The way that you read it is actually going to be, people read it in 2 ways. One is they say 6, choose 2, and let's just leave it at that because we are running out of time here. So I'm just going to say that this is one way of reading this, 6, choose 2. And what 6 choose 2, a way to evaluate what 6 choose 2 is to take the 6, the first number, and you're going to do that factorial, and then it's over, then you're going to do the difference of the 2, which is 6 minus 2 factorial, and then you're going to finish up with the second number, which in this case is the 2 factorial. And that hopefully is an expression that you can evaluate. If you can't, it just takes a little bit of practice. I'm not going to take time to do it here. I might have a little discussion on this 6 choose 2 business at another time so that we can go into some more depth on that alone. And it plays a role here with the binomial expansion, but it's really its own separate topic, and we can do a lesson on that. Now watch this. I got the 6 choose 2. Now it's going to be 6 choose on all of the coefficients, and then you're just going to grab the exponent. So this 3 here, if you're looking up to the right there, that 3, I'm going to choose that, and I'm going to include that with my combination calculation. And then I'm going to go on to this last one down on the left, and that's going to be 6 choose 2. And actually, I might have confused you a little bit here because the thing is I could take the 2 or the 4 in this previous one. So if you look at this, I'm allowed to take the 4 or the 2. It doesn't matter. They're equivalent if I take the 4 or the 2, but I probably should have stayed consistent and just taken the 4. So I'm going to put a 4 in there. All right. Now, I'm not going to evaluate these. Again, we could get these from all of these coefficients from Pascal's triangle. We could use this method of evaluating them here. We could use that. And then there's also a calculator key-in. On any scientific calculator, there is an NCR key, which is N choose R, right? A generalization of that. On any Inspire, any graphing utility, you're going to be able to find out where you can key these in. Again, that's a lesson for another video or something that we'll take a look at in class. But with that, you should be able to expand, and then of course there's a lot of other things we want to simplify here. But that is a good introduction to binomial expansion, and we might look at more of it. You might see more of it in class or in additional videos.